Good morning. Today's topic will be discussing about the chemistry of coordination compounds. The coordination complexes involves metal and ligands. Metals usually are positive charged, which are capable of accepting electrons, and ligands are usually negative ligands, and there are also positive ligand and negative ligands. Ligands are capable of donating electrons to form the bond between metals and ligands. Few examples of metals are iron, copper, chromium, zinc, silver, platinum, palladium, etc. And few examples of ligands are chlorine, bromine, iodine, fluorine, sulfate, nitrate, nitrite, cyanide, carbonate, ammonium, etc. The nomenclature of coordination compounds are quite different from that of the normal compounds. They can be differentiated by the sounds. For example, bromine will be pronounced as bromo, chlorine will be pronounced as chloro, cyanide as cyano, fluorine as fluoro, etc. And it goes on. In coordination complexes, there are anionic complexes and cationic complexes. Usually, anionic complexes will have the charges as negative, and anionic complexes will have the charges as positive when it comes to the oxidation state. Let me give some IUPAC names. The example will take the cobalt complex. In the cobalt complex, we have 5 ligands of amine group and 1 ligands of chlorine group. And outside the coordination sphere, let us take 2 chlorine atoms. Now let us see how to name these coordination complex. Since the oxidation state of this cobalt is 3 through the calculation, we shall name the oxidation state with the Roman letter 3, and hence the IUPAC name goes as pentaamine, since we have 5 amine groups. Then followed by chlorine. Instead of chlorine, we have to pronounce it as chloro. And this is all about the metal and the ligands present inside the coordination sphere. And the outside the coordination sphere, we have chlorine. It is not necessary to indicate it as di or mono or whatever. It can be simply pronounced as chloride. Now the IUPAC name is pentaamine chloro cobalt 3 chloride, and this is quite simple to name the IUPAC name for all the complexes. Now there are few theories which explain the coordination complexes. Few of them are Werner's theory, Sidgwick's theory, Pauling's valency bond theory, crystal field theory. Let us start with Werner's theory, and this theory actually differentiates primary valency ligands with that of the secondary valency ligands. Primary valency ligands are the ligands which are present inside the coordination sphere. Primary valency ligands are present outside the coordination sphere. And the ligands, when it is present outside the coordination sphere, they correspond to the oxidation number. They are ionizable, they are non-directional, that is, they can be present in any direction, thereby donating the electrons to the central metal atom. And they are usually negative ligands. When talking about the secondary valency ligands, they are present inside the coordination sphere, and that is why they correspond to the coordination number of the complex. They are non-ionizable and they are directional, that is, they are present inside the coordination sphere, and they must be negative ligands, which in turn provides the proper geometry of the coordination complex, and hence they are non-ionizable and they are directional, and they are usually negative ligands or neutral ligands. Werner's theory actually predicts the color of the complexes. Say for example, we'll take this picture. When the chlorine atoms, when they are present just in the planar mode, the color of the complex is given here, it is yellow. When the ligand it is present opposite in direction, the color changes. And also when few of the ligands, when it is present outside the coordination sphere, the color goes on changing. And this shows the beauty of the coordination complex. Now let us pass on to the Sidgwick's theory. Sidgwick's theory actually proposes the stability of the complex. In other words, we can explain it as when following EAN rule through the calculation, if your answer matches with the atomic number of the noble gases, the complex will be stable. If it does not match the atomic number of the coordination complexes, the metal will keep on accepting the electrons. That is, it will keep on accepting the electron from the ligands, and the metal will be capable of forming bond with the incoming ligands. For this, Sidgwick proposed the formula using EAN, that it is effective atomic number. The formula is Z minus X plus N into Y, where Z explains the atomic number, X is oxidation number, N implies the number of ligands, and Y implies the number of electrons donated by each electron. So through this calculation, we can calculate the effective atomic rule, the number of each complex. So the examples are given here in this slide. For the iron 2 complex, the answer is 36, which matches with that of the noble gas atomic number. Hence, this complex will be stable. The second complex, ferricyanide, through the EAN formula, the answer is 35, and hence it is unstable. But this ion is capable of accepting one more ligand to match the stability of the complex. This coordination complex can also predict the hybridization and the geometry of the complex. There can be 2 ligands, 3 ligands, more than 6, etc. If it is linear, the hybridization is sp. And if it is triangle, there are 3 ligands present, the hybridization will be sp2. And it goes on like octahedral, the hybridization will be d2sp3 or sp3d2. When the hybridization is d2sp3, it is implied as inner octahedral, and when the hybridization is sp3d2, it is implied as outer octahedral complex. So for the complexes with 4 ligands, it can be differentiated between square planar and tetrahedral. When 4 ligands are present with the hybridization of sp3, the geometry is tetrahedral. When it is dsp2, the geometry is square planar. Thank you.